Okay, now you should be able to see my slides. Is that okay? Do you see the slides?
Yeah, it's good.
Yes. Okay, perfect. Okay, so thanks and welcome everyone. So I will give you an overview of protein dynamics and Markov modeling. We start with an example from protein simulation. So this is a small protein system that we have worked on a couple of years ago. From a biological point of view, it's very small and simple and well studied, but it's still something that is very hard to simulate extensively using an all-atom resolution. This is Barnase and Basta, two proteins, two small proteins. One is the inhibitor for the other protein. So they must bind, and they bind very tightly because the inhibitory complex is supposed to be stable. In an all-atom simulation, this is about 100,000 atoms. And now this is, of course, something which we can model in the computer. So we have an energy function, for example, charm or ember. And then we have bound and unbound states and perhaps some intermediates. And in principle, this gives rise to a probability distribution, such as the Boltzmann distribution in the canonical ensemble that we would like to sample in order to compute, for example, what's the probability of being bound or being unbound at certain conditions. And we can do that by running MD simulations. And on a decent GPU, this will take about 1 week per microsecond that we get. But unfortunately, the binding process for this system in this concentration, so in this box size, takes about 50 microseconds for one binding event. So that's a GPU year. Of course, we can parallelize that and just do 50 times 1 microsecond and hope we get one binding event and then compute statistics. But the reverse process is much, much slower because the inhibitory complex is stable. It will take about 1 hour or more in real time. So in simulation time, in wall clock time, to simulate this process, that corresponds to about 1 million GPU years. And that we cannot get out of just by doing parallelization. So we need some tricks in order to be able to compute this process at all. And so Markov state modeling is one of these tricks that we can use. And we need several others, but I'll show you later what we've done there. So let's do some basics first. The idea in Markov state models is that we represent a relatively complex process which has atoms in a macromolecule plus solvent moving in 3 dimensions and in 3 continuous coordinates for each atom. So we're moving in a high dimensional, 3 n-dimensional state space that is continuous. And we somehow want to represent this with a very simple process, namely a Markov chain jumping between discrete states, and not too many discrete states, maybe 100 discrete states, maybe even 1,000, maybe 1,000, something in this order, but not millions or billions. Okay, and the reason why this often works, or why it even can work, is that there is a separation in time scale, at least in many of the processes that we are interested in. So here's a very simple system. This is butane, which basically has this rotation around the torsion angle in the middle. And that is slower than the other motions here, slower than the rotations of the methyls, slower than the vibrations and oscillations of bond lengths and angles, etc. So there's one slow process which switches between these different conformations shown in different colors, and there is fast stuff. This is not always nicely separated. Sometimes we have slow processes and fast processes, and there is not a pronounced gap between them. That can happen. But in any case, we often have the aim of resolving the slow processes in a molecular system, such as protein folding, protein ligand binding, protein binding, slow conformation changes in the shape of the binding pocket, for example, opening of allosteric pockets and things like that. This is, of course, not only valid for protein dynamics. Essentially, in all nanoscopic systems that are somehow driven by noise. So also, if you have, let's say, if you're simulating heterogeneous catalysis and you have atoms that are being adsorbed to a surface and then can react with one another, then you have slow processes there too. For example, maybe the diffusion process, the jump process of certain adsorbents is slow, or the formation of particular structure or the dissociation of particular structures is slow. So this is pretty much ubiquitous in molecular science. So we want a method that can simplify these dynamics, keep the slow processes, and throw away the fast stuff, and throw away a lot of the complexity with the fast stuff. Okay, of course we lose something when we do that. Every model has to do some sort of approximation. So we will lose certain things. So if you want to compute properties which depend on the fast processes, you cannot do this anymore after you've discarded them. Okay, when we want to compute properties of molecular simulations, it's important to keep in mind it's always about statistics. The individual trajectory and what this one trajectory has done first and second and third is not important. What is important is statistics. So that means probabilities that our system is at a certain part in state space, correlation functions, so things like that. So averages that we can compute when integrating over all positions in state space or all trajectory realizations of our dynamics. Okay, so the stationary distribution, that's often something that we're interested in because we want to compute equilibrium expectation values, and for this we need the stationary distribution. So in many cases, this is the Boltzmann distribution. Boltzmann distribution is given for the canonical ensemble, so constant temperature, volume, and particle number. But of course, we could have other ensembles like constant pressure ensemble, for example. But in any case, we have some sort of probability distribution defined by the energy function that we're using. And we can, in principle, for every energy that we can compute for a given molecular configuration, we can compute the probability density, but we do not have the normalization constant. So we cannot normalize this function. Yeah? So this is the partition function. This is something we can normally not compute. And basically all methods in physical chemistry or molecular sciences are trying to avoid doing this. Okay, so now meaningful quantities to compute are, for example, expectation values. So the probability of a certain observable A in this ensemble with equilibrium distribution mu. That's the, for example, the Boltzmann distribution. So that's an integral. Also interesting, for example, are correlation functions. So this is the time correlation between observables A and B at time lag t. And so this is weighted by the probability to find the starting point in A. Sorry, the starting point in X, and then we evaluate A at X. And the probability that from X we go to Y, so to another state Y in that time tau. And then we evaluate B at, sorry, this should be a Y, B of Y. Okay, so these are examples for expectation values that we can compute, and from that we can compute a lot of things that are practically interesting, like the folding free energies, binding free energies, folding rates, binding rates, unbinding rates, etc. Now, why is this hard? So it's hard because although I said, well, we can for every x, we can compute the probability density at this x, but we cannot easily sample it. Yeah, so we cannot simply enumerate all the possible positions of a molecule and then compute the probability density, and then just normalize it by the number of points we've computed and thereby solve this problem. That's not possible because our space is much too high dimensional, and most states that we could potentially generate by putting atoms somewhere in space have essentially zero probability. Because atoms are clashing, bonds are stretched or whatever. Most of the states here have ridiculously high energies or small probabilities. And this is the sampling problem. We have this high-dimensional space. Very, very few places in this high-dimensional state space actually have meaningful energies and probability densities. And this is why we use molecular dynamics or Markov chain Monte Carlo to explore this probability density. We start at a reasonable starting point, like a protein crystal structure. And then we move a little bit in small steps, and we only make steps such that we stay in high probability regions. And the cost of that is, of course, when there is another region of high probability, let's say we start from a folded state and then there's an unfolded state out there, which also has a significant probability. But in between there are states, there are transition states with small probability, and it's very hard to cross them. And these are rare events, so this is the sampling problem. Okay, so how can we make this easier? So we can rewrite the expectation value of a function a, so of an observable a, equivalently in this form. That's the same as the integral I've shown you before, it's just reorganized. And we have now introduced a partition with n states. So we have partitioned the state space into n states, S1 to Sn. Yeah, index those with I. And now every state I has a probability to be in. That's just the integral over all of the probabilities in the state. Yeah, so that's the probability to be in equilibrium in that state I. And then I just execute the integral, the expectation value over that state. And I just have to divide the probabilities here by pi I, because I'm eventually just summing them up. Yeah, so I can now turn my expectation value into such a sum, a discrete sum over probability to be in that state and the expectation value in that state. Let's say A is a fluorescence, and I'm looking at protein folding, and I've prepared my protein such that it shines light when the protein is in the folded state, and it's dark when it's in the open state. And I just do a two-state Markov model. Then I just have a sum over two states with probability of folded times fluorescent in the folded state plus probability of unfolded times fluorescent in the unfolded state, which is 0 or 1. Okay, so that's the same calculation. Why is this making things easier? Well, one thing is that the integral, which is here, that's now something we can hopefully much easier compute than the previous integral, because we only integrate over states. If we have done the partition well, we only integrate over states that equilibrate quickly. So when the transition between folding and unfolding is slow, but the diffusion and oscillations in the folded state and in the unfolded state are each fast, then this integral can be quickly computed. We don't need very long trajectories or map very many trajectories to do that. So the problem has now shifted to computing this PI, so the probability that we are in each state in equilibrium. But for these PIs, for these pi's, we can derive another function, another equation. So we can find that the probability to be in any of these states, so I'll just write all of the pi's, the probability vector bold pi. This pi is the equilibrium distribution of a Markov chain. So if I have Markov chain transition matrix, which tells me what is the probability that my system would switch from any state I to any state j in a given time tau, and then independently of which time tau I choose, and that can be a short time, something that I can still easily simulate, then this will give rise to a stationary probability, and those stationary probabilities, this is now a vector, so those are discrete, those are just the ones that I can insert here. So if I can compute this transition probability matrix, and then again, this is an expectation value, more efficiently than just running a very long trajectory and essentially get a histogram of mu by counting, then I've won something. And this is exactly the case here. And the reason is why I'm winning something. Computing this pi here only depends on conditional statistics. P is a conditional statistic, so it captures what is the probability that at a certain time later I will be in this or that state, given that I start here. Right, so when I have like 5 states, I could in principle start 5 simulations or 5 times 1000 simulations in each of these 5 states and just run trajectories that are relatively short, maybe a nanosecond or 10 or 100 nanoseconds. And then after that simulation time, count how many of them stayed in this state or went to another of these 5 states. And from that, I compute an estimate of my transition matrix. Whereas if I want to do all of this without transition matrix, I have to start somewhere and I have to run a very long trajectory that manages to transition between all of the 5 states often enough so that the statistics, how often have I been in every state, is converged. So I have to do everything with super long trajectories, and I can either do this only with very, very simple and small systems, such as maybe peptides or small proteins, and then it still takes very long. I can do it with larger systems if I have access to, let's say, an Anton supercomputer, but there are not too many of them in the world. But if I want to parallelize that problem and do that on a GPU cluster with 100 GPUs, and that's much easier to get. I can maybe get AWS compute time and do that in the cloud. Then I need some sort of trick to decompose the problem, and that's one of these tricks. Okay, so that's the basic idea here. Now we can understand the equations that were shown that we have in principle a continuous dynamics which propagates my continuous states. So my states in a 3n-dimensional state space propagated in time via the molecular dynamics engine we're using. And we discretize that in some way in state space, but also we discretize in time. So a Markov state model is essentially a time-space discretization of the underlying dynamics. So a bit of history. So much of the foundation of Markov state models was laid in this paper here from 1999 by Christoph Schütte and co-workers. Christoph is in Berlin. He's the president of the Zuse Institute, and because of this wonderful work, this was actually one of the main reasons why I moved to Berlin. And then the next couple of years, we started extending Markov state models and making them usable for molecules. So in the early days, in the late 90s, it was mainly like ideas and benchmark systems and mathematics. And then we really wanted to do things like peptide folding and protein folding. And in the first years of Markov state modeling, and here are 2 papers back to back in JCP with my friend John Codera that are representing this era, we were thinking, okay, based on what I just told you, we should just discretize the state space into a few states such that they have long lifetimes. Because essentially of the argument that when you're in the state and the system has long lifetime within the state, it will lose memory of where it came from. And because we lose memory, it's reasonable to approximate this process with a Markov chain, because a Markov chain doesn't have memory, or it has a memory of 1 step. So it only remembers essentially the last step. Okay. And that's a reasonable argument, but it didn't necessarily lead to the best Markov state models. And in order to understand how to do Markov state models better and to understand many of the algorithms that came later, it's very important to understand this slide. And this slide says essentially, really what we have here is continuous dynamics, and that can be described as the action of a propagator on a probability density. Okay, what does that mean? So the probability density describes what is the probability to find a molecule anywhere in state space at any given time. If you start simulations only from a particular folded structure of the protein, then this probability density is a delta peak on that folded state. And this here, the propagator just describes what happens statistically if you apply a molecular dynamic simulation to that. So let's say you start with that delta peak at that one structure, and now you run 1,000 molecular dynamic simulations in parallel for a certain length, for 1 nanosecond, let's say. So because these simulations are stochastic, they have thermostats in them, and maybe different initial velocities, they will evolve not exactly the same. They will all lead to slightly different endpoints. So after these 1,000 simulations, we asked the question, where did these simulations end up? And that's the new probability density. And they will probably still be folded or mostly folded. But if we run the simulation long enough, then perhaps some of them did unfold. So we have a probability density which has some folded, some unfolded in it, and it's somehow a function which describes in state space where we are. And this here is really the limit of infinitely many simulations. Yeah, we're not doing this in practice, but this is the idea. The idea is we have a probability distribution of molecules. We run infinitely many simulations from each state. We ask where we end up. Okay, this is of course a theoretical construction, but the important insight is that in this theoretical construction, we can rewrite the action of this propagator in such a spectral decomposition. What does that mean? The dynamics underlying, the molecular dynamics that is propagating states here and that's moving molecules around can be written as a sum of exponentially decaying functions. Yeah, so the change in the probability function, in the probability density, has some sort of basis set, if you like. These psi I are functions that you can just combine in order to express any change of the probability density in the future. And this here is a scalar product between these functions and the starting distribution. So it's just a number, just a coefficient. And this is an exponentially decaying function. E to the minus tau ki. Ki is a rate, or the inverse is a time scale. Okay, let's look at an example. So we have this 4-well energy landscape. And let's just do a diffusion in this 4-well landscape. So it's intuitively clear that most of the time we will be at the energy minima. We will be fusing around here. And we will rarely jump across these transition states. So we'll have a probability distribution in equilibrium that is something like this. Now, if we look at the spectral decomposition of the dynamics on this energy landscape, it has 4 eigenvalues, and the eigenvalues are, in fact, these things here. So e to the minus tau k, that's an eigenvalue. 4 that are close to 1, and then there's a gap, and then many fast ones. And that is because there are essentially 4 slow, long-lived states in this system. So we have 4 energy minima, 4 metastable states, and we have 4 large eigenvalues. And then we have a lot of fast stuff, which is the local oscillation and vibration within the states. We also see in the structure of the transition matrix there are these 4 blobs, which represent the fact that there is a high probability to stay in a certain part of state space when we're there. Okay, and the eigenfunctions, so psi are the eigenfunctions. So they tell us, all right, there is one eigenfunction that is constant here. We can actually multiply it with the equilibrium probability, and then we just get the equilibrium probability. So this first eigenfunction, which has an eigenvalue of 1 means it never decays in time. That is a stationary process. So we can always compute the stationary probability from our Markov chain. Now the second makes a jump here in the middle. That means there is a second process, a relaxation process in time, which is slow. So this is not exactly 1, it's a little bit smaller than 1. That means it has a rate kappa that is small, close to 0, or it has a time scale, so inverse kappa, that is large. And at this time scale, probability is shifting from AB to CD, or inverse. So if you're here on the left, then on the slowest time scale, you're going to the right. The slowest process is the one that goes across the highest transition state, which is intuitive in this picture. And then the next slowest process is for shuffling probability from A to B across this next lower transition state, and then from C to D. That's the blue process. And in one dimensions, that's all clear and obvious, and you wouldn't need this analysis. But if you have a high dimensional system and you are simulating, let's say, peptide folding, and it's very hard to tell what's going on, and you have a lot of data, so looking at the video is really not an option. And it's not immediately clear which are the relevant coordinates or the descriptors that will inform you of what are the slower interesting processes. Maybe it's RMS root mean square deviation to some reference structure, but maybe it's something else. Maybe there's a proline flip somewhere which makes the dynamics slow, and that does have nothing to do with folding. So if you want to find this out in high dimensions, then essentially what you want to do is you want to be able to compute a model that gives you some information of what the eigenvalues and eigenvectors or eigenfunctions are, so that you can find the long-lived processes and the slow transitions. And Markov state models are exactly that. Okay, another consequence of this analysis is that really what matters when we want to have a good Markov state model is not necessarily to just have, let's say, 4 states in this example and have them exactly with these boundaries. That would be still a good or a decent Markov state model. But the goal really is to approximate these eigenfunctions and eigenvalues as good as possible. And that you can do if you use more states than 4. So in a 2-state example, if you use just, if you have 2 energy minima in a continuous space and you just 2 Markov states to approximate them, that means you approximate this eigenfunction that switches between these 2 states, which is the red function, with such a black step function. And you're still making an error here, and that means that the time scales or the transition rates between the states that you get from a Markov state model are wrong. They're not bad, but they have some error. They have some approximation error, and they're usually too fast. But if we approximate the same system with more states, so we just have additional states, especially around the transition state, that divide the system into finer substates, we get a better approximation. So we make a smaller error, even though none of these states here are long-lived. Yeah, because it's not about long-livedness, it's about, so this Markovian argument, we must be sure to forget where we came from quickly. It's a valid argument, but it's not the argument that leads to the best Markov state model. Yeah, what leads to the best Markov state model? It's find the best approximation of the eigenfunctions and eigenvalues. Okay, so now in practice, we would like to have a recipe which does this for us. Because, I mean, the pragmatic approach would be now to just use more states. And that's, if you only look at this side of the argument, that's okay. But of course, if you use more and more states and you have a fixed amount of data, that means your statistics are getting worse and worse. And I haven't talked about statistics at all. So there's certainly an optimum between using few states and poorly resolving your slow processes, and using as many states as you have trajectory frames. And at that point, you basically have no statistics that make any sense. You may not even have a connected Markov chain. So it must be somewhere in between. So what is so first we want an optimal, theoretically optimal approach to find these eigenfunctions and eigenvalues. And interestingly, we can derive a variational principle. So that's like in quantum mechanics. In quantum mechanics, you also have an operator, the Hamilton operator, and you often are interested in computing eigenfunctions and eigenvalues of this operator. The wave function, for example, the ground state wave function and the ground state energy. And you have a variational principle, and if you use a method like Fock, you're computing the variationally computing solutions to that. And here we have a similar variational principle. So we can prove that the first eigenfunctions are the solution of this problem that we can actually compute in practice. So we take functions that are ansatz functions or trial functions. And these trial functions could be, whatever you can compute from your molecule. Distances, contacts, contact indicators, angles, any of this stuff, descriptors. And we just compute them for all the data, the molecular dynamics simulation data we have stored, and we compute time correlations of these descriptors. And the theorem says those descriptors which give us the maximum autocorrelation function in a certain time step tau, with some constraints. This is just that these functions need to be normalized and have zero mean. And then the maximum is, if we find the maximum, then these descriptors will be identical to the eigenfunction. So then these are exactly describing our slow processes. And now, of course, you cannot hope to directly achieve this if you just fix certain descriptors, like distances or angles, because it's probably a mixture of certain things. It's a collective variable. And this is why you now need to use this principle in order to find the mixtures of the descriptors that you can think of. And let's say we just want a linear combination of descriptors, such as bonds, bond lengths, angles, distances, contacts. We just write those basically in a library. And we ask, what are the coefficients to mix these descriptors to collective coordinates, such that these collective coordinates are really the best slow coordinates. Now it turns out, again, we have to compute covariance matrices of these descriptors. So the instantaneous covariance matrix, that's the same like in PCA, and the time lag covariance matrix. Then we have to solve this generalized eigenvalue problem, which is a normal eigenvalue problem if we use Z0 inverse C tau on the left as a matrix. And then the eigenvectors and eigenvalues of this, so the eigenvectors of this eigenvalue problem are our coefficients. So they tell us how our molecular features should be combined to give the best approximation of the slow processes. And this is then the space of slow processes. So that's the space in which we can build a very nice Markov model. Okay, this is just a formulation of the algorithm, but let me give you an example. So here is a time series, 10-dimensional time series. And there are actually slow processes in this time series, but it's very hard to see that in these 10 variables. Now I can do a principal component analysis on this time series, and I will now, of course, order processes. I will find collective processes that have more and less variance and order them. But it doesn't really help me to see that there are any slow processes or slow rare transitions. But if I use this method, the variational approach, I can separate the processes in which there are slow events from the processes that are just random noise. And in fact, what happened here is that we took these time series here. So we took 3 processes that have slow switching in them, and we just added 7 dimensions which are noise. And then we mixed these 10 dimensions in a random way, so using a random 10 by 10 matrix. And then that's what we get. So think of this, what's happening in your protein or whatever high dimensional dynamical system you're looking at. There are some slow processes hidden in this mess. It may be something local. It may be a transition around a torsion angle somewhere. Or it may be something more complicated, like several torsion angles moving together in a concerted fashion and switching between 2 states in which a loop of the protein has different conformations. It may be something obvious, like ligand goes in, ligand goes out. But it could be something that's really hard to see, even if you look at the video, even if you have time to do that. This is a systematic method to extract this information from very high dimension data. Okay, so the simple algorithm to implement this method is TICA, time-lagged independent component analysis. And here's just an example of how TICA can find the separation of 2 probability densities that are very close by, but that transition slowly from one to the other in this vertical direction, whereas PCA would just find this direction as a main direction, and then if you project the data onto the PCA direction, then these 2 densities overlap, whereas TICA can separate them. Okay, so TICA, if you want to build MSMs in the now traditional way, I would say TICA is sort of the first step. So you first look for the slow subspace to reduce the dimension and still keep the stuff in which you can find your slow processes. Then the second step would be somehow discretizing, for example, using clustering that space, which is now easier because it's lower dimensional space, and estimating your transition metrics. And that I'm not going into detail because there's quite a bit of detail on that in the course otherwise. And then you can analyze the resulting transition metrics. For example, you can compute transition path theory if you're interested in the probability of certain transition pathways in going, for example, from the unfolded to the folded state. You want to have the parallel pathways that fold the protein, and you want to understand what is the probability of taking each pathway. And these are all things you can compute with a Markov model given. So with a given transition matrix and the given partition of the state space into the states used by the Markov chain. Okay, so here are certain examples. So this is from a protein simulation of ligand binding to a protein, benzamidine to trypsin. Benzamidine is an inhibitor to trypsin. And here is a reducible coarse-grained transition matrix. So that was, we computed a Markov state model with more states than these 5 states, but then collected all the states that belong to the same metastable set to have basically an easier way to visualize what's going on. And here the different colors are the different metastable sets. They are now mostly in the ligand space, so basically unbound, bound to a pocket which is not the main binding pocket, and then different places to be bound to the binding pocket, and then really bound inside the binding pocket. Those are the different states. Here are transition probabilities on a certain time step. And here is the result of transition path theory. So starting from the unbound state, going into the bound state, and you see there are direct trajectories, and there are trajectories that, let's say, go to this yellow state, and then you diffuse on the protein surface to this state, and this state into this state. So these mechanistic analysis and insights you can then get from the Markov state model. Here's another example where we've done that with this is an HIV protease, and it's the terminus of the chain binding to the binding site of the HIV protease, where it is cleaved. This is an enzyme which cuts proteins, basically, and it's part of the HIV protein chain in the virus. And these basically all the proteins coming in one chain, and then this protease, when the virus matures, has to start cutting it into its individual pieces so that these proteins can do their work. And this is why this is a one protein that you can use as a drug target. To inhibit this protein means to basically stop the virus from working. Okay, and then with the transition path theory analysis, you can get a mechanistic idea of how this process works and what are the different parallel paths. Okay, there's this review book from 2013. It's quite old now, but the basics are still all correct. The application sections maybe are not so interesting anymore, but the basics and the theory is still, of course, correct. Here is the PyEMMA sources, but also the deep time sources are, of course, very important for this workshop. Then maybe to wrap up, I just want to say this you will also see more of tomorrow. You can, let me go quickly here. Instead of going through this pipeline that I just described, doing TICA, clustering, estimating your Markov state model, coarse-graining your Markov state model, etc. There are now deep learning versions of doing this whole thing in an end-to-end framework. So, for example, we have developed VAMP nets, and VAMP, so first of all, VAMP is basically an extension of this variational approach I described earlier to you. So it is a variational approach, which is trying to find somehow the best Markov state model. And in some cases, so in the case that we have equilibrium dynamics, and we're not pulling the protein, we are not putting energy into the system, we're just simulating it at equilibrium. This is actually identical to the variational approach we described before, but this variational approach is more general. So this one variational approach is more general. It can also be used for non-equilibrium dynamics, and then for this reason, it can also be used for other types of dynamical systems than protein simulations or molecular simulations. But the point is that you use your trajectory data as an input. So you take trajectory points at xt and xt plus tau. So if you have, let's say, 1 million frames that have been saved from your simulations, and that corresponds to a certain length, let's say 1 microsecond. And now you want to build a Markov model in 1 nanosecond lag time. So that's 1,000 frames in your at your saving rate. Then you always take frame 1, frame 1001, frame 2, frame 1002, etc. You take all these pairs, so you have almost 1 million pairs, 999,000 pairs. And these can be given as an input to your neural network. Now, the neural network is trained using the variational approach. So basically, it goes through several layers. The purpose of these layers is that they find basically a dimension reduction. They're trying to find out what is a good way to compute nonlinear collective coordinates from my input, such that my output will best resolve the slow processes by maximizing the time autocorrelation on them. And this is how you train your neural network. And then when you have this, and when you define your output neural network layer as a so-called softmax layer, so that's a classification layer basically, where each neuron has a probability that your system is in one of these neurons. These neurons correspond to long-lived states. Then you can directly compute a Markov state model from that. You can directly compute a transition matrix from that. So that means you get a transition matrix that is variationally optimal and a state space partition, because here this neural network is now a classifier that assigns each state in state space to a Markov state by training a deep neural network. Okay, and this can give very high quality and high accuracy neural networks. And you'll hear more about that later. Finally, we want to go back to our friends, Barney Sparsta. So we can do MD simulations of individual, starting from different states, from different initial structures, bound, unbound. And we can do that. We can compute Markov state models from the data that we have generated, but we will not get a connected Markov state model from that alone. So what we've done here in this paper is adaptive sampling. That means we decide based on the current model and certain statistics, like how many counts do we have in each of these states. Did we just find a new state, for example, that we haven't left yet? Based on that, we start new simulation data in states where we believe we still have not enough statistics. And we also use more than 5 states to do that. So this is kind of the final analysis of these 5 states. But if we do this, we can actually accelerate these slow processes, because we can, in a way, push the system up the energy barrier from the bound state to the unbound state, and vice versa. And by pushing up, I do not mean to use a force. Yeah? It's still equilibrium molecular dynamics. So we're not using non-equilibrium molecular dynamics. All the transitions we see in the data are completely unbiased equilibrium dynamics. It's just that the starting points from which they begin are not from an equilibrium distribution, but that is something we can fix with the Markov state model, because it reweights the states with respect to one another. Right? And so with this trick, we can get a complete statistics of binding and unbinding with 2 milliseconds of data, which is still a lot, but it's a lot better than ours. It's many orders of magnitude better than ours. And so this is actually feasible on a GPU cluster in a couple of weeks. And here is a binding trajectory where the proteins first associate and then they diffuse on each other's surface until they eventually find the bound state. Okay, so this is you can make your simulation data you can use your simulation data much more efficiently using Markov state models. It still takes a lot of simulation data to get a good Markov state model, but that is just an indicator for the fact that your simulation data is always the problem. There's always a sampling problem. So if you use another analysis than a Markov state model, and it looks much better, and you don't have problems with disconnectivity, etc., that's just because that other method is just hiding the problems. Yeah? That's very important to understand. This is a way to analyze what you have. It's a very powerful diagnosis tool. Yeah. So if the diagnosis tool tells you there's a problem with your data, and another diagnosis tool tells you there's no problem, that means that the other diagnosis tool is just lacking the resolution. So very often, any kind of problem people have with building Markov state models is not enough data. And the Markov state model itself can just help you to point out where the problem is. It doesn't solve that problem. It solves it a little bit because it helps you a little bit with it, because you can use conditional statistics. You can use simulations that start from different starting states and not necessarily from an equilibrium distribution. Yeah, but when you're just missing transitions, you're missing transitions. And the only way to do this is to go back and collect more data. But the Markov state model can tell you where the missing transitions are and how you can collect more data. You can leverage it to improve the simulation data. So in this particular example, we needed 20,000 GPU days to get the answer, or 500 gigajoule, which is a lot of energy. If you compare it with the rocket launch of a Saturn V rocket, which is 1500 gigajoule. So this is probably not the end of the story. You can do more. You can definitely do more by combining, for example, enhanced simulations, which use some sort of biases or higher temperatures or whatever, with the unbiased simulations, and combine that with the Markov state model. So there's the TRAM method, the transition-based reweighting analysis method to do that. That's also implemented in PyEMMA. Not in deep time yet, but in PyEMMA. And we're also working on deep learning methods, such as generative neural networks, to try sampling the Boltzmann distribution directly without going to single steps of molecular dynamics simulation. And we have some initial results on that, and you can read it up here in the science paper 2 years ago, Boltzmann generators. There are some ideas, and there are many more ideas by other groups out there. So I think it's a very exciting time. A lot is moving. Machine learning has given us a lot of tools to make progress in areas where progress has been very slow the years before. And with that, I'm finished. This is a overview of my group, or at least part of my group, post-COVID state. Moritz is, I think, not in this card deck, but he's here in reality. So with that, thank you for your attention, and I'm happy to take questions. Any questions?